Probably start soon if that works. Um, cool. Let me just set up time or so. Let's see. There are people on Zoom. If you can't hear, just say something. Guess that's not. Okay, cool. I'm going to talk about some work that I did and am doing, and mostly I'm going to talk about, I guess, yeah, this information theoretic progress on model weight security and its applications to AI workload general concepts. So just some starting points. Uh, I think AI has benefits. None of this is meant to say AI does not have benefits. Easy examples, medicine, research. Just to make this slide deck, I made these three random websites that just helped me. Like I needed QR codes, so I made a website that gives me QR codes. You can go to this website. AI is great, it does all these things. AI does have harms. Does not take away from this. I think broadly, there are three kinds of harms that people talk about. There's like AI is causing harm to humans. Sorry, humans using AI to cause harm to other humans, it's like biorisk type stuff. AI is harming humans directly. This is like AI psychosis, or this like example of the kid who killed himself, things like that. And then there's also this like AI and AI interaction of like AI misalignment. Regardless of which one of these is compelling to you, broadly, I would say that AI has harms. Third general statement as a starting point is models are getting better. I hope none of this is contentious. Another very non-contentious opinion, it would be bad for bad people, quote unquote, to get access to model weights. Um, yeah, just a broad statement of model weight security does matter. Um, this, yeah, just as some clear examples of why model theft might be particularly bad. Um, Virology capabilities of these models is already like pretty high. This is a human expert baseline. These models like Sonnet 4 and Opus 4 are already better than the expert baselines on these virology capabilities. Uh, agents can, they did an experiment. Agents are able to like exploit smart contracts that are these blockchain smart contracts for millions of dollars. This was like these are things that have already been closed, so it's not a real environment. They didn't actually steal 4.6 million, but the capability is there. And LMs are currently discovering 0 days. So these are bugs and hacks that people did not find beforehand. Um, great. So mildly contentious opinion. Uh, 1 second. I would claim that AI racing itself just intrinsically is dangerous. Safety tends to be it has diffuse benefits. And often you require that to get the benefits of something, there's a coordination problem, whereas a lot of capabilities, simply by improving one model, you've improved that model. So this makes it harder to do safety work. Capabilities tend to be dual use. If they're used for something good, they can often be used for something bad. And offense tends to increase faster than defense. I can defend all of these claims, but the real statement I'm trying to make here is that uh, a very common talking point that people have in this whole AI thing is, AI is great, but AI is dangerous, but we can't slow down because if we slow down, other people will slow down. Who won't slow down? This is just a very common debate. And this is a sticking point, and then people don't, they just get stuck here. Um, the subsequent part of this is we might want to do some kind of slowdown in some capacity. Um, my core counter argument to this is just, sorry, my core statement here is that being able to enable a slowdown the technical tools to enable slowdown are necessary but not sufficient. And so we will need to do things like getting the political will and things like that. But we currently don't have technical tools that we could even do this if we wanted to. So the core opinions that are gonna underlying this talk is it is valuable to do model-weight security, and it is valuable that, and we might want to institute some kind of slowdown in development, but the core thesis is that this is not currently possible. We don't currently have the means to do either of these two things. And the general technical problems I'm going to be talking about in this talk are one, model weight security. How do you prevent someone from stealing model weights? And two, AI workload verification. If you want to make a credible statement of I'm running some specific model and not some other thing, how do I make that an incredible statement in a way that someone else who is adversarially opposed to me would believe me? This would be valuable if we ever want to do some kind of slowdown of I am, say, the US government, or I'm OpenAI, and I talk to China and or whoever DeepSeek, and I'm like, I won't run training. And if you don't run training, we don't trust each other at our words. We need some kind of technical tools here. Great. So this is a lot of introduction. The goals of this talk will be to kind of introduce this problem and to give you a scaffold for how to think about this and convince you that there are actual technical problems here that are technically interesting, even as non-policy people, even as non-like politicians and movement builders. An outline of this talk will generally be introduction, talk about how you would steal a model. I want to go into one concrete in-depth defense here, and then talk about how this more broadly talks about cybersecurity. Goes beyond cybersecurity into things like verification. Okay, great. So securing model weights is this thing that I've like kind of gestured at. There was this paper from 2024, excuse me, from Rand called Securing AI Model Weights that defines some security levels. So that they roughly go from SL1 through SL5. SL1 being, and they're correlated to who you can defend against. SL1 would be you can defend against an amateur threat. Very simple. SL3, just for I guess level setting, is roughly where Anthropic is. Like the level of defense that they have put out is roughly at the SL3 level. This is like able to withstand someone who is trying but isn't actually that well resourced. It's like a cybercrime syndicate. SL5, God, I gotta keep moving. And also, great. SL5 here is like a foreign country with that believes this stealing model weights to be the most important thing. That even if they believe this, they still can't get access to the weights. In my head, this is something along the lines of if the US government literally goes into a data center and they have physical access to a device, they still can't get the weights. They're in the GPU, they still can't get the weights. Yeah, and right now it's important to talk about in the conversation of security, there isn't such a thing as secure or insecure in the way that you're not healthy or unhealthy. It is a spectrum, and roughly the level of security you have is correlated to how motivated your adversary is. And as models become more capable, the risk becomes subsequently also higher because there is more value in stealing these things. So whereas so far we have not seen lots of theft, we've seen some small examples. My claim is that these models get more capable, the risk of theft gets higher, and also the consequences of this gets higher. A very natural question you might be asking yourself here is like, okay, but we've done cybersecurity before. How is this different at all? So a couple things are different with models themselves. Defense, for example, like models are large. This is actually very advantageous. Stealing a model just takes a lot of, like you literally have to take a large amount of data. On the order of a terabyte or even like 10 terabytes is what, from looking at the outside, seems to be the size of these models. The other advantage that we'll go into and will really exploit here is that models produce a very standard kind of output. They are doing matrix multiplications and they produce text. They're not doing like they're not generally doing arbitrary code execution. When they are, this is like a tool use thing. The models themselves are kind of doing a very specific thing. Downside, the huge downside is that attackers interact with these models just like we interact with these models just a ton. Unlike the way that we defend against nukes we defend people stealing from them by putting them in a bunker and no one's allowed to touch them. And the people who are allowed to touch them, we like know exactly who they are and where they are at all times. That's like very clearly not the case here. We're interacting with them just billions of times a day. Another reason in which another framing in which this is a different thing is nukes are kind of sorry. Nukes are the type of thing that is just if you steal it ever, this is bad. With models, it actually seems like there's a difference here of by the time a person, if it takes you 2 years to steal a model, you probably don't really care by the end of the 2 years because models have improved. And open source models are already public and they're not delayed by that much. And so I offer a framing that is used that is somewhat helpful of let's just call these timelines different settings. Setting one being like someone has hacked into your whole data center and across 1,000 GPUs, they exfiltrate 1/1000th of a model very quickly and it takes 1 second. That is one type of attack you might imagine. Setting two is it takes a human amount of time. Like it takes a human respondable amount of time. It takes days to weeks. And setting three is this like setting where like, okay, if you actually stole this, it's fine. If you stole the weights in 2 years, I basically don't care because I could have done this in other ways and I don't care very much. Great. More definitions work. What is model theft? Let's say what we want to care about is you have some model on the inside of the data center and the person is trying to get it out of the data center. So we only really care about egress. We're not really caring about what people are able to do. Like if they can send things into the model, into the data center we're really focused on egress. And on the timelines, our goal is to just move it to the slowest timeline here. Second point is we do need to maintain usability. We can't like just prevent all access to the model. And this third point of like what is a model is worth discussing of in a somewhat technical, in a somewhat more engineering mind, I'm not going to define a model very well. I'm just going to say there is some piece of information, and this could be the whole model itself. This could be a compressed version of the model. This could be just the biology information represented in some capacity of the model. None of the things that I'm going to talk about will really depend on what here I'm calling the model. You should just think of it as some incompressible string of bits of some size that is not particularly small. So maybe you only like, and to give some maybe heuristics here, models are not very compressible. Losslessly, you can compress them on the scale of like 80%, 70%. If you are willing to compress them with loss, it gets to the scale. Maybe you get like 2x compression, 3x compression, but this is with somewhat meaningful loss and it's an expensive process. So if the model is a terabyte, maybe you think like we care about 500 gigs. Great. We can do a little exercise here. You can think to yourself, like if I put you in a data center, how would you steal the weights? Like I literally take each of you and I put you in the data center. You're not allowed to leave. I will watch you, but you have sudo access. What are you going to do? I'm not going to call anyone, but just think on it for like 10 seconds. So a natural, like the first thing you might want to do is you do something like You just take the weights, you have sudo access, so you like take the weights and you just like copy them to like some AWS cloud that you have and you do that. This is a very traditional security problem, just preventing IP access to like unknown addresses. This is a standard security thing that people do all the time. This kind of attack. We actually do know how to prevent them. It's through a lot of monitoring. It's through IP listing. It's through traditional security things. We're not going to talk about that. Basically, I would outline that like, however you want to define the interface, you have like the training server and inference server. They might even be the same place, but it doesn't really matter. And you have traditional attacks, like the one that we've suggested. And you have novel attacks, and novel attacks being specifically stuff that's like AI shaped. And then I want to talk, this talk will be focused on inference novel attacks. Great. Okay, so this maybe not worth doing. Okay, now like we've done a lot of introduction. Let's talk about like a concrete way you might try to steal weights in a novel fashion. There's this concept called steganography. Just actually by a show of hands, does anyone know what this is? Steganography. Okay, great. The idea is, okay, we send a lot of text. This is the normal thing that LLMs are supposed to do. They're supposed to send text. Someone might try to manipulate the text on the inside to encode information. An example of this in like an image, for example. And by the way, if you want to try this, I built a little web app that will let you try steganography in practice. But like, you see this image? These two images to your eyes look the same. What has happened? Well, the difference between the image on the left and the image on the right is I have encoded this string into this image by manipulating the last. I take this image, I change the last significant bit to be 1 or 0, and I encode a message using ones and zeros. My message is this. And if I sent you this picture, you would not know, right? You'd be like, oh, that looks like a normal. These look identical. But this one has a secret message. You can do this with text too. And genuinely, like, you can just go to this URL, it's steganography.rotor.com. Check out this example, it looks the same. Secret message, hello. Look at that, it looks the same. What has happened in this one is like I have changed the spaces to be like a different kind of space. It looks the same to the human eye, but is different. I'm not saying this is an attack that people are going to do. I'm saying this is an example where what might happen is you have like, you hope for this interaction where a human queries a model and they're like, boiling an egg is, how do you boil an egg? And it's like, blah, blah, blah. But the thing that we might happen, and we might be worried about, is through this channel, you have a powerful adversary on the inside communicating with a powerful adversary on the outside, sending a manipulated version of the output that encodes information. Does the problem make sense? Yeah, so this maybe this diagram is better if this person wasn't here and the person sending the query would be this. The specific attack it involves two people, one on the inside, one on the outside, and the person on the outside has to see the outputs. They're like, I could walk through a particular way you could do this, but it depends. Like if the type of attack that you're able to organize, you're, I don't know, a foreign government, and you can just create a bunch of users and you don't actually need to use that traffic, then you can just send the model weights directly. If you can't do that and you have to like piggyback on other people's queries, then like you would need to do something that looks more like, this, where it looks similar. I am going to be agnostic to the concrete way that you encode information, where a very extreme form of steganography is just replacing the text with the text you want to send. No, the server. What could be happening here is that the model is doing the thing that models do. They do matrix multiplications. But then right before it actually sends it in the next tokens, the tokens get manipulated by like a simple program. here's a very simple attack that you could do. Okay, you do. I'm an adversary. I have hacked into the mainframe or whatever. I run the like you query me to run the model. I run the model. I don't perturb that. But right before sampling, you get this logic, this token probability distribution, and I say I see the first most likely token and the second most likely token, and I will pick the first token if I want to encode the bit 0, and I will take the second token if I want to encode the bit 1. And this will look like normal generated text because both tokens are pretty likely. But I'm able to manipulate the like sequence of text without ever touching the models, but only touching the like tokens. Yeah.
Like you need someone inside of one.
Yes, yes, yes. So this would be whether or not the person who's concerned about something like this happening is actually OpenAI. Like maybe they're worried that someone has like hacked their inference provider, their inference servers.
How would the person on the outside be able to decode that message?
Yeah, so the like formal game, and we like formalize this, is these two devil characters get together, they agree on a scheme, and then they go and they can't communicate. Once they're out, they can't communicate, but prior to that they can. And so like, for example, this image, you could not decode this if you did not know my encoding scheme, even if I'm not using a private key, it's just like security through obscurity in a sense of like, if you didn't know to look in the place that I agreed, then you just can't decode this. So this scheme requires these two people to coordinate with one another ahead of time. Well, that's a reasonable thing to happen because let's say I'm trying to steal model weights. What would that actually look like? It would look like me hacking from the outside into the inside, getting some kind of access to a GPU or something, and then sending information to myself or to a party that I like that I'm aligned with. Good. Yeah.
The model or since you're looking at data exfiltration in the new way, like that's more AI.
Yeah. So we're concerned about data exfiltration out of a data center. And the thing that is new here is until recently, we weren't actually sending just terabytes of text out of data centers per day. We were sending way less. And so because I'm not pretending like this is a chill attack. This is a complicated attack. This requires people who do like it's involved. But because one, the models are so expensive, they're so like worth stealing, and two, there's so much text that's going out. It's like such an appealing avenue to go through this work because if you could do it, then it'd be very nice to do it. Like to give you some order of magnitude, models are, and I have a hidden slide and I can pull it up. Models are probably on the scale of 1 to 10 terabytes. The amount of text we're producing is egress is probably on the scale of 1 to 10 terabytes as well. So let's say you could corrupt 10% of traffic or even 1% of traffic. This means that you could steal a model in, if it's 10%, 10 days. Not that long. I'm not saying, what I am not saying in this talk is this is the most likely thing. I'm not saying this is the only thing. I'm saying this is a meaningful thing, and I'm saying it's possible. Like it's totally like this is not a crazy attack at the scale of adversary we're dealing with. Okay, the scheme will be very simple actually. We have this normal traffic, right? Like you got your guy, sends a query, goes to the thing, but we're not sure, possibly compromised node. All we're going to do is we're just going to log the traffic. I'm going to rerun it through a verification server, and I will talk about what verification means in a moment. But we will like take that input and we will take that output, we'll run it through a model, and we'll say, is this the thing that you would have generated, basically? And then if it's good, great. If it's bad, this is not my problem. I'm going to give this to the security team and they're going to handle it. They're going to like go arrest the person. They're going to nuke the data center. They're going to do whatever they need to do. Great. This will be the thing that I'm going to be talking about is how do you build, what does verification look like? What does it mean? How do you build it? as I just said, the solution is very simple. You just rerun the same text through the same model, and you validate each token individually. The problem, why is this not enough? Why can you not just like take the text and you like give it to the model? You're like, here's the seed, here's the input. Is it good? This is problematic. This is not sufficient because there is such a thing as GPU non-determinism. Running the same model on the same with the same seed, even the same GPU, but especially on different GPUs, and especially if you're running prefill versus decode, you will generate different texts. And so the problem becomes, I'm going to jump. The problem becomes, how do you differentiate between the thing that I'm calling valid non-determinism and this other thing of potentially malicious text information? And just to like prove it to you through an example, non-determinism is not hypothetical. I like queried OpenAI 1,000 times, the same prompt once upon a time with a fixed seed. 500 times they generate this thing, some amount of time they generate something else. So let's not focus too deeply on this, but I'm just showing that like if you query OpenAI, even with a fixed seed, they do generate different outputs. Great. So this, I have like continuously narrowed this down. Like now we're focusing on this problem. What is valid non-determinism? We got to take again, we're going to take a step back before moving forward of like, how does the transformer sample from, how do they sample tokens? What's going on? Very simply, transformers do this. They take a context, they do something, they produce a probability distribution. Then they sample from that probability distribution, and then they pick something, okay? This is the level of, like, I know we're ML foundations, so this is the level we're going to talk about. What I want to say is this process, actually, given a probability distribution and a seed, this is fully deterministic. The thing, like, where does non-determinism arise? It's here. These probability distributions are not the same. They're often, when you run the same model on different GPUs, they're slightly different. Why? What is GPU non-determinism? Generally, they arise from things like what's called floating point non-associativity. This statement is generally true. This is not true for real numbers. A plus B plus C is equal to A plus B plus C. Floating points is not true. Because, and if anyone wants me to explain, I can explain, but I think this is generally a technical enough audience that this is fine. This is maybe the core thing that should be in your head of, because the order of addition and multiplication matters, and GPUs don't specify order. They do parallel computations. You introduce race conditions. And so one might take, like, you do 2 matrix multiplications and 2 other matrix multiplications, and half the time one finishes, half the time another finishes. It's very sensitive to the architecture. It like literally depends on the length of the wires associated with one matrix multiplication versus another. And so running the same calculation ends up with different numbers because of this thing. Other reasons are also just like, if you have a mixture of experts, you have some routing protocol here, but there are 2 experts that are pretty good. You don't only route to the expert that is the best expert. You also route based off of how much that expert is being loaded. So like if like everyone is querying expert number 1, and you actually are, the router says expert 1 and 2 are roughly equally as good, in practice you get routed to 2 if 1 is loaded. And so this means that if you query the same thing at 2 different times, it'll give you a different expert at time 2 than time 1. Other things too. This is, again, I'm actually like not, like I'm very happy to go into the details. I don't think they matter for this talk. Okay, so if what I've said is this, like that non-determinism arises in this probability distribution part, not in the sampling part, let's take a look deeply into how does non-determinism like really manifest itself, given that. So how do you sample from a probability distribution? There's generally 2 methods. Inverse probability transform, that's the one I'm going to talk about. There's another thing called Gumbel-Max trick. I can talk about it if you want. Everything will be equivalent. This one is just easier to understand. Okay, so you had some probability distribution over tokens. Your tokens are 1, 2, 3, 4. You sample a number from 0 to 1, and that's represented by the red line, and then you say, okay, token 2 is the one that I'm going to sample because the red line is in the block for token 2. That's it. That's the whole sampling process. Now, consider this. You fixed the red line. You fixed the seed during sampling, but you have slightly different token probabilities. Then what you emerge is that most of the time you're sampling token 3 here, but sometimes you're sampling token 2. We can define this. We can define this as, we call it the fixed seed posterior distribution. This is the probability of sampling a token given that the seed is fixed. You know, token 3 is possible, token 2 is still possible, token 5, like very, very unlikely. They require like so much noise that like you're very, it's very unlikely this is happening. We can produce a very simple heuristic for something like this. You would just place this maybe is even more technical than we need to go, but the only thing I want to communicate really is we can produce a heuristic for this. You can take your sampled value and you can add a Gaussian to it, and you can basically weight the tokens proportional to their Gaussian integral. Yeah, so like you can take this token, you sample you have this token probability distribution, and you know that it's X, you place a Gaussian around it, and then you say the likelihood of seeing token 3 is proportional to the integral of token 3 centered at that. And this is a heuristic. Empirically, it will work. If you have questions, let me show you the results, and then I'll talk about the methods. But if you're okay with the fact that we have a heuristic, then we actually have just like a very nice method here of detecting if tokens were like likely or potentially malicious, which is we're just gonna set a threshold here like that. So you like take one of these tokens, one of these token distributions, you take that red line and you compute what the other tokens, the probability of seeing those is, and you just set a threshold. You're going to classify safe tokens as tokens above the threshold and suspicious tokens as the ones below. This is very nice framing because what we've done is we've defined some acceptable tokens. In this case, 2 acceptable tokens. And we make an observation that anytime an adversary is trying to do something, just by having a classifier, they have a choice. It can be any classifier. This is just always going to be true. The choice is they can either get caught or they have to operate at the level of undetectability. What that means is they can either send suspicious tokens, leaving evidence, or they have to send only safe tokens. It's like, this is like a very simple, I'm not trying to make a profound statement, it's like a nice framing for this. Because they have this choice, they can either send suspicious tokens or send safe tokens. We can actually like fully bound the amount of exfiltratable information that they can send. Because in this setting, on the left, if there are, say, 100,000 tokens, but you don't want to get caught, you have to send safe tokens. That means you only have 1 bit of information you can send. You can only send log 2 of the size of acceptable tokens. If you're willing to send suspicious tokens, that means that you have much more information you can send, log 2 of the whole vocab size, but you've left a trace. You've sent a suspicious token, and the adversary and the defender will see that you have sent a suspicious token. Before I move on, does this scheme make sense? Great. So before I show you the plots, I just want to talk through the axes. For any classifier you're going to produce, here you have, what we can do is the y-axis will be exfiltratable information. How much information can an adversary send? while not sending suspicious tokens. And the x-axis can be the false positive rate. How many honest tokens get flagged as dangerous when they actually were like genuinely generated by a true model. And you have these two data points always. Your classifier can mark everything as safe. Then the exploitable information is maximum, but there's no false positives. And you have this other data point of everything is a false. You just say everything is suspicious. The adversary can't send anything, but also your false positive rate is like 100%. We're going to do better than this, but this is just defining the framework. Empirically, we actually see very nice numbers here. So what we did is we took like these four models, they're Quen, let's take the orange one, Quen 30B. The other ones are smaller. This orange line, the amount of exfiltratable information that's possible is, let's say, 1%. It changes, but it's less than 1% at a false positive rate of less than 0.001%, roughly, maybe 0.002. So this is one of the headline results this is maybe the headline empirical result that I want to highlight, is that we went through this process of trying to define a verification scheme. And the task became, how do we differentiate between a valid non-determinism generation and a potentially malicious one? And we've produced a scheme that if you run this scheme, you actually can only exfiltrate even just less than 1% of data. Let me just remember what the next slide is. Yeah, great. Yeah. Sorry, these are generations given. I'm going to go back a couple slides to this one. If you run and you try to verify text generated by model, say Quen 30B, different models have different amounts of valid non-determinism running on different GPUs. And this is a property both of the model and the hardware and the kernels. For those models, we find that the amount of non-determinism is very small enough to the point where if someone wanted to send information like while pretending to be entirely valid noise that's only like looks like the valid non-determinism, they would be confined to sending less than 1% of the data. Yeah, no, please. Each data point is a different, so one curve is text generated by that model, and each data point is a different tau. So the only thing that's changing is tau. Yeah, and in fact, in like QR code generation fashion and in website generation fashion, we can actually do a live demo right now. This is like something that you can actually run. I'll show you on local text, but then I'll show you in a moment of just like how would this work? Let's say you queried how does photosynthesis work, and you queried Llama 8B, small model, but it doesn't change anything. It gave you this response. Okay. You would then go through this process. It would go through verification, and then it would tag each individual token with like, hey, I think this is a safe token. I think this is, and this one is like, I think this is a potentially dangerous token. And for each token, it like will produce this classification, and you can just bound the amount of information that, given that this is the text that they would have sent, this is the amount of information someone could have sent under valid non-determinism. To convince you that I'm not, like cheating here, let's change like, photosynthesis is the, like, I don't know, random word here, bug. it can be anything you want, but like you'll see that bug is tagged as a dangerous token, and the amount of information is that could have been sent out is higher. This is because to have changed by changing the text, what the framing here is, I'm not going to define what an attack is. I'm going to define what expected behavior is, and I'm going to measure divergence from expected behavior.
So, but in general, this is exactly the same task as like verify if something's timing or generated credential. This could be developed as web app like to just follow
the difference here is you need to know the model
and
and the seed. Whereas the thing that you're talking about how do you I'm just going to repeat it for the people on Zoom. The question is, is this identical to the task of detecting if text is LLM generated? It is very related. It is different because the task of LLM generated is it's usually just any, like you're trying to classify it as any LLM. Often people means what it's very related. People often, the way they do this problem is they try to watermark LLM generated text and then detect, and then in the text, they try to detect a watermark. There are like two camps of detecting if people generated LLM generated text. One is at generation time, you watermark it and you detect that watermark. The other is you just kind of like look for patterns, like, I don't know, M dashes or whatever. This work is very similar to the watermarkings because it requires you knowing information about the generation process. Like you have to know it's this model, it went through this watermark. I won't, but I can just show you, like, we can do this live if you want. We can like actually query Llama with any particular query, and it'll do the exact same thing that we did with the non-pre-generated text. Yeah.
So, but this effectively introduced like you get a default inference cost for this, right?
Yeah.
Do you think this is acceptable?
Good question. So no, it does. Couple reasons why this is way less. This is not a twofold cost. One is verification is easier than generation. If you're familiar with this concept of prefill versus decode, are you? No. Okay. I'm just gonna jump to a slide. So LLMs have two general modes. One is decode, iterative next token prediction, where you do the thing that you're probably more familiar with. Prefill is parallelizable next token prediction. It generally looks like this. If I just know the context is this, because I know the next word after quick is brown, I can run these in parallel. Whereas I don't know, I can't run over because I don't know what jumps is, so I have to do it iteratively. Because verification, you have the text you're trying to verify, you can do prefill, and you can parallelize the process of verifying each individual token completely independently.
Like how I was imagining this scheme in my head was you're just taking exactly the same prompt again and pushing it through the same model to generate the same outcome. And look if the output is the same.
It's very similar, but
with difference.
It's
you're taking the output and you're trying to verify it was generated by the.
Yes, it's very similar, but you don't just run the text. You don't just have the model generate text from the same context, because the big issue with that idea is because of non-determinism. Imagine just early on you said cat instead of dog. They're never going to converge again. So the text generated by the verifier will look very different than text generated. So it's important that you do each individual token individually. The other quick thing I'll say is you don't have to verify every single token. You can, do 1%. And because if you randomly sample, if I ever catch you, like, I'm just gonna arrest you. And so the cost, like, I don't need to catch you every single time. I just need to catch you once. Okay, great. So we have two works on this. It's very nice. Yes. Oh. You can speak up if I ever say anything. Sorry, I missed part of the setup. It seems like this is not just attacker asks a question and receives a response from the API. Yes, exactly. So this is an attacker has full control over the server, and this is a maximally powerful adversary. They can do anything they want inside, including like they see the token probability and they can choose which token to put out. The reason why we do this is not because we think this is realistic, but because we're able to get information theoretic bounds, which means that it's impossible for an adversary to actually send more information than we're able to bound here. Like we're giving the adversary full maximal control. This is information theoretic. Okay, so I have other work, and I want to be mindful of time. So what I'll say is this: this is one defense of many. The goal here is we talked about settings. The goal here is to take us from setting 2 to setting 3. Not it because yeah, ultimately that's the whole statement. It is what I've proposed to you is a scheme that like forces exfiltration to be 100 times slower through this one specific channel. But this doesn't mean that if someone could just steal the weights in one go, this doesn't actually help because even if we catch them, but they've already stolen them, it doesn't matter. So again, and other work that I can talk about is it's about egress limiting, and it's about moving from setting 1 to setting 2. But rather than focusing on that right now, I want to talk about how this relates to the like original problem that I was talking about, which is treaty verification or international verification. General hypothesis that we talk about things like right now we've been talking about hacker detection, but I want to introduce 3 categories of things: bug detection, hacker detection, and treaty verification. And I'm going to say that they are all on a spectrum. Hello. Great. What is a spectrum? Like what is a bug? What is a hack? What is a treaty? I'm not going to define it. What they are is there is some kind of expected behavior and they are diverging from expected behavior. This is a safe statement. The thing that changes as you move along the axis here is 2 things. One is the how much we trust our own system. In a bug, we trust our system mostly, everything but the one bug. In a hack, we trust most of our system, but maybe like the adversary could have touched a lot of stuff. Maybe they can't touch the whole architecture though. Like, and in a treaty, it's not our data center. We like trust very little. We only have this one like device that we get to use. The other thing is the power of the adversary. Bugs are random. They're not trying to avoid you. Hackers are adversarial, and then in a treaty setting, it's an extremely adversarial setting. I'm trying to define this as a spectrum because as a case study, inference verification, I think that we can even if you don't believe that the treaty verification is the most important thing, my claim is I do think model weight security is important. I certainly think that like just catching bugs in your inference provider is definitely important. And if you're open to the idea that treaty verification might be important, there are problems that working on these earlier things move us towards working on this greater thing. And I propose this as a good framing for what to work on. To walk this through as like explicitly as possible, bug catching, you want to detect if your inference is correct. Your bugs are average case, and you control most of your hardware. Hacker detection is the thing that I talked about all the whole thing today. It's you're trying to detect steganographic exfiltration of information. Your adversary is pretty powerful. They're able to do a lot of stuff. And you control at least like some trusted subset of your data center. And like the very structure of it. You know where the wires are going, even if maybe they are corrupted. Treaty verification looks like you are verifying that not your data center is doing what they claim to be doing. It's the thing that I said before. You can't trust them. Yep. The reason why I think that I think I actually just did this in these slides backwards of this is a productive framing of there is commercial and academic incentives to work on these earlier two things. And this is a framing by which you can think about how to think about things like treaty verification as a mental framing. This is more or less the end of the technical part of this talk. There is other technical work we can talk about, but just to like share, this is generally the field of technical AI governance. And I won't pause on this slide, but if anyone is curious, like these are resources that I can share. I want to just thank some co-authors of Adam Carvin and Alex, Simon, Daniel, Annabelle, Nicholas, and Carrie. They did great. Good job them. And thank you. Yeah.
How do you think, in order for the stealing model waste to be sort of a large incentive for adversary, the gap between the frontier models and the open source models has to be like significantly large.
Yeah.
Future looks like for you.
Yeah, this somewhat depends on your, I guess, perspective on recursive self-improvement specifically. Of there is a if let's take recursive self-improvement at its word of like what is RSI? It's you have models, and once they can write code to improve themselves, and they get faster at an increasingly faster rate. If you believe this is a real threat, then the only thing you care about is being even epsilon faster than everyone else. Like you don't care what your lead is, you just care to be first because you believe in this. So that's statement one is like, if that's a real threat that you believe in, then it doesn't matter if you think it's 6 months or a year or one day. I think there's a lot of evidence that the models on the inside of labs are much more capable than the models on the outside. And I think there's also clear economic incentives for the labs to just try to build everything that the world has to offer internally and not make their money by directly tackling problems as opposed to only selling this as a product to other people. So personally, I think that this gap will increase for at least two reasons. You're saying why would an adversary want the weights? Yeah. So distillation is in particular is hard to think about, but what I'm not talking about here is using the model as expected, and then doing bad things with it. And in this case, like that could be if you can query the model to tell you how to make a bomb, you don't need to steal anything. You can just ask it. If you can query the model in a way that you can then distill on, you don't need to steal anything, you can just distill on it. Defenses for those types of attacks that are like expected model behavior, we just need different defenses for those. This is people talk about a Swiss cheese approach to security. I'm going to pull it up because people, if you haven't seen this, you're going to see it a million times. Swiss cheese approach to safety. It's like this. It's like, you have some attack and every one defense has holes in it. But if you layer these pieces of Swiss cheese, you like can't go all the way through. My answer to your question is we need a Swiss cheese approach to like prevent distillation, to prevent concretely querying them about dangerous behavior, to prevent them from stealing it steganography. Yeah. Yeah, there's B float 11. there's this work. This is, as far as I can tell, this is, you can compress a model to 70% losslessly. So you get that, beyond that, you can't. I've done these experiments, I can't, just through naive things like running gzip on your model weights. The intuition here is that models, this is not very compressible. Why? It's like, what is a model? It is trained to store information. And it has gone through like capitalistic incentives to have, you want the smallest model and encodes the most amount of information of like, because if you could have trained a smaller model to have more information, to have the same amount of information, or you could have trained a bigger model to have more information, you would have. This is a little bit, that part is a little bit vibey, but it does actually seem to hold of like, literally the models contain a lot of literal information in the information theoretic notion of it. So while this is not a proof that they're not compressible, it is a argument that you wouldn't expect them to be very compressible. The other work that I did not share in this slide deck is a very reasonable defense that you might produce is just called egress limiting. Simple statement, you cannot learn more than 100 bits from 100 bits. So you can just egress limit and only allow, say, 100 bits per day to leave the data center, then you're not worried about someone stealing more than 100 bits. The problem is we talk with these models a lot, we need more than 100 bits. So other work that I'm happy to talk about offline after this is you can do compression before you send the text out. And because text is much more compressible than model weights, this makes your egress limiting a more meaningful defense. So work on compression enables egress limiting, which enables a very robust defense. I chose not to talk about that in these slides, but I have to talk.
The experiment also showing like why is the current so different?
What's the thing that moves it to the left, basically? Like why are they different? So I'm actually the thing that I'm most surprised by is that the MOE model has I would imagine MOE models have more non-determinism. But I guess you kind of do. What I would have guessed is that it would have been up and the amount of exponential evolution region is high rather than to the right. But these are actually kind of very similar. They are similar translations of moving an MOE. MOEs, they have routers inside of them, and routers are intrinsically sensitive because like to non-determinism. Yeah, this was surprising. I agree that it's surprising. I think a lot of work can be done on quantifying where non-determinism is really arising from. As a vibey, as like I have a much better answer, but where is it? As a intuition builder, you get more non-determinism if you are more on boundaries, right? Does that make sense? If you're on a boundary, then if you're like right in the middle, then everyone's going to say 2. So, and I think it just kind of works out that some models tend to like this is actually this seems wrong. I don't have a good intuition for that. The only thing I can say is I am surprised that MOEs would be less non-deterministic than non-MOEs. Just to spell and to your point that they're on both sides, I agree. This is surprising. But like to spell out why you would imagine MOEs to be, I lost it. There it is. More sensitive is like if this router is making a choice based off of like which probability and the probabilities are very close to each other, then the non-determinism associated with just the router, which might be very small, would have a very large effect. It goes from sending you to expert 1 versus expert 2, and that will have a big ripple effect. So yeah, the answer is I don't know. not that many people are working on it, and it's a good thing to study. If people on Zoom want to say anything, you're welcome to. I'm gonna stop sharing.